December 7, 1942. The Solomon Sea boiled under black clouds and cannon fire. Japanese dive bombers screamed down through the overcast, engines howling as tracer rounds tore the sky apart. On the deck of the USS Helena, 19-year-old gunner William "Red" Turner braced against the recoil of his 5-inch gun. His shirt clung to his back with sweat and seawater. Around him, sailors yelled over the thunder, range, fuse, fire, voices raw from smoke and fear. 200 yards! Timer set! Fire! The gun slammed backward. A blinding flash. A shell hurled skyward, vanishing into the chaos. Red didn't look up. He'd seen it before, the same hollow pattern. Black bursts too early, too late, too far. The Japanese planes cut straight through the flak, steady, fearless, precise. Another scream overhead. A bomb hit near the stern. The deck lurched, flames sprayed oil and salt water across his face. The gun crew scrambled for ammunition, hands burned raw from the heat of the steel shells. Every man was doing his job. Every shell missed. By sunset, the Helena had fired almost 5,000 rounds, not a single confirmed hit. That wasn't because they lacked courage. It was because the math didn't work. Anti-aircraft fire in 1942 hit less than 1% of its targets. A single 5-inch shell cost $20 to make, 100 more to ship and load, and almost everyone exploded harmlessly in open air. Entire convoys fired until their barrels glowed red, only to watch enemy aircraft drop bombs with surgical accuracy. The U.S. Navy called it area defense. The men called it what it was: luck. The problem was time. Each shell carried a simple mechanical fuse, a tiny clockwork mechanism that had to be set by hand before firing. The gunner estimated how long the shell should fly before detonating. The higher the plane, the longer the timer. The faster it moved, the shorter. Every adjustment depended on judgment, guesswork, and nerves. At 300 miles per hour, a difference of half a second meant a miss by hundreds of feet. Once the shell left the barrel, there was no correction. A second too early, it burst harmlessly below. A second too late, it exploded in empty sky. The Japanese pilots knew it. They called the American flak the fireworks. German pilots said the same thing over Europe. Allied shells filled the air with smoke, but rarely danger. British gunners defending London in 1941 needed 20,000 rounds to bring down one bomber. Their guns thundered night after night, yet the Luftwaffe kept coming. On the Helena, Red Turner had stopped watching the sky. He just reloaded, set the fuse, and fired again. He could feel the futility in every movement. When the battle ended, he wrote 3 words in his notebook: "They don't work." He wasn't alone. Across every front, Allied commanders were beginning to see it, the limits of their own technology. The gun crews were brave, the weapons powerful, but the timing was blind. No amount of training could overcome the basic fact that human reflexes couldn't match modern warfare. In Washington, military analysts had started running the numbers. The statistics were humiliating. Thousands of shells, millions of dollars, and barely any effect. The reports were stamped confidential, but read the same every time: ineffective at altitude, inaccurate at speed. The truth was simple and deadly. The Allies could not stop an air attack once it began. Their best defense was to throw steel into the sky and hope probability decided to cooperate. In Tokyo, Japanese officers read intercepted reports with amusement. In Berlin, Luftwaffe engineers studied captured shells and dismissed them as psychological weapons. Everyone thought the same thing. The Allies were drowning in their own industry, building weapons that made noise instead of results. But inside a small cluster of labs in Maryland, a group of American scientists saw those same reports and came to a different conclusion. The problem wasn't bravery or manufacturing, it was design. At the Applied Physics Laboratory, physicist Merle Tuve stood over a workbench covered in fragments of shattered glass and copper wire. He held what was left of a vacuum tube, a component that had once powered a radar transmitter. It had been fired from a test gun that morning. The force of launch, 20,000 times gravity, had crushed it instantly. Someone asked him if it was even possible to build a radar that could survive that. Tuve didn't look up. "It has to be," he said. "Otherwise, we're finished." Radar at the time filled entire rooms. Each unit needed heavy coils, transformers, and fragile glass tubes that shattered if dropped from a desk. Now the Navy wanted something small enough to fit inside a 5-inch shell, tough enough to survive launch, fast enough to detect an aircraft in flight, and smart enough to explode at the right moment, automatically. A radar brain in a bullet. To most engineers, it sounded insane. To Tuve and his team, it sounded like the only chance left. The concept was simple to explain and impossible to build. A shell that could sense a target. Instead of a timer, it would emit a faint radio signal, measure the reflection from nearby metal, and detonate when the echo grew strong, when it was close enough to kill. No human guesswork, no setting dials under fire. They called it the variable time fuse. The name was deliberately boring, chosen to hide its purpose from spies and even other American agencies. Later, history would call it what it truly was, the proximity fuse. Early tests were a disaster. Some shells exploded in the barrel, destroying the test mounts. Others flew perfectly, but never detonated. Engineers worked in thick flak vests, knowing that one miscalculation could turn the lab into a crater. The shock of each failure rattled windows for miles. Still, they kept going. Each failed test told them something: a weak solder joint, a shattered filament, a misaligned circuit. Dozens of prototypes were built and destroyed. They learned how to cushion vacuum tubes with wax, how to reinforce the glass, how to use the shell's spin to power a tiny generator inside. Bit by bit, the impossible began to look merely improbable. In March 1943, a drone test took place off the coast of Virginia. A small plane, remotely piloted, flew at a steady altitude. Below, a Navy destroyer tracked it and fired a single experimental shell. The observers expected another miss. They raised their binoculars just in time to see a flash bloom within 50 feet of the target. The drone wobbled, caught fire, and fell into the sea. No one spoke. Then the range officer whispered, "That's it. That's the future." It was the first working proximity fuse in history. Back on the Helena, Red Turner didn't know any of this. He was still loading, still firing, still watching bombs fall. The Navy didn't tell its sailors about secret labs or new technology. But within months, the work of those engineers would reach his hands. The new shells looked the same, gray, heavy, harmless, but they were different inside. Instead of a brass timer, they carried a living circuit. The first shipments went to the Pacific, disguised in plain crates marked simply VT. No one outside the project understood what those letters meant. What Red and thousands like him would soon discover was that the war had just turned. The proximity fuse changed everything it touched. It transformed flak from noise into precision. For the first time, gunners could fire blind and still hit. Shells no longer had to pass directly through a target. They only had to come close. And close was something the U.S. Navy had in infinite supply. But in late 1942, that victory still lay ahead. On the front lines, the men fought with weapons that didn't work and hoped that barely held. Every battle was a coin toss, every bombardment a prayer. When Red watched another Japanese plane dive through the smoke, he didn't see the hidden revolution happening thousands of miles away. He only saw the bright line of the bomb falling, the moment before impact, the heat on his face. He didn't know that somewhere in Maryland, a woman at a soldering bench was building the first circuit that would save him. She wasn't a soldier. She didn't wear a uniform. Her name wasn't classified in any report, but the fuse she built would one day make every pilot in the Pacific afraid to come within a mile of a U.S. ship. The men on the Helena didn't know it yet, but the age of guesswork was ending. Within a year, the ocean that had swallowed their shells would become a killing ground. The same hands that had twisted dials in vain would soon hold shells that could think. And when they fired, the sky itself would start doing the math. The war had been ruled by chance. Soon it would belong to calculation. The proximity fuse was coming, and it would make every old rule of air combat obsolete. Spring 1943. The world was on fire from both ends. In the Atlantic, German submarines sank Allied convoys faster than American shipyards could replace them. In the Pacific, Japan's air raids had turned the ocean into a graveyard of burning steel. The word defense meant very little when every known weapon failed against speed and altitude. And yet, in a set of low brick buildings in Maryland, a group of civilians had been asked to build something that sounded like lunacy, a radar system small enough to fit inside an artillery shell. The man in charge was Merle Tuve, a 36-year-old physicist with a calm voice and no patience for bureaucracy. His team wasn't composed of soldiers or factory managers, but of scientists, engineers, radio technicians, and women who had never been near a battlefield. What united them was a single, impossible sentence: make a shell that can see. Tuve's people worked for the newly formed Applied Physics Laboratory, technically a division of Johns Hopkins University, but functionally an arm of the U.S. Navy's desperation. Their workshop was half laboratory, half junkyard, benches covered in soldering irons, coils, broken glass, and burned paper. Nobody wore uniforms. Half of them didn't even wear lab coats. They worked 16-hour days surrounded by test shells, circuit diagrams, and the constant smell of ozone. At first, the problem wasn't technology. It was physics. A 5-inch anti-aircraft shell experienced 20,000 Gs of acceleration the moment it left the gun. That meant every component inside had to survive forces equal to 20,000 times its own weight. A human skull would liquefy under 100 Gs. Most machines broke under 1,000. Nothing built by man was designed to withstand 20,000. A normal vacuum tube shattered just from being dropped on a concrete floor. Tuve needed one that could survive the violence of launch, function flawlessly while spinning 500 revolutions per second, and still detect a target by radio echo. His first solution was crude, a tiny metal case packed with wax to absorb the shock. It didn't work. The glass still cracked. The circuits tore loose. The failures came daily. Engineers fired test rounds at a nearby proving range, then dug through the mud for fragments. Every piece told a story: a blown capacitor, a melted filament, a circuit shorted by centrifugal force. They collected data like archaeologists collecting bones. The Navy had little faith. Admirals didn't understand the details, but they understood the cost. Millions of dollars, no results. Some wanted to cancel the project, but Tuve refused to stop. "We're not building a miracle," he told them. "We're fixing a clock." He wasn't wrong. The proximity fuse wasn't magic. It was timing perfected by physics. The principle was simple. A small transmitter would emit continuous radio pulses as the shell flew through the air. When those pulses bounced off a nearby object, an aircraft for instance, the reflected signal would interfere with the outgoing one, creating a beat frequency. The fuse would detect that interference, recognize it as proximity, and trigger detonation automatically. No timer, no guesswork, just the laws of electromagnetism. What made it revolutionary was scale. The entire radar unit had to fit in the nose of the shell, smaller than a man's fist, and run off a tiny battery that had to survive months in storage and still work in freezing air at 20,000 feet. It had to be mass-producible by the thousands and cheap enough that commanders wouldn't hesitate to use it. Tuve divided his people into specialized groups. Some worked on miniaturization of the circuits. Others redesigned the power supply. A small team of women, mostly mathematicians and radio operators, focused on calculating the frequencies most effective for metal detection. They didn't know it at the time, but their calculations would later form the foundation of post-war radar engineering. The government's secrecy was absolute. Workers were told only what they needed to know. The letters VT were stamped on blueprints and shells, but no one explained what they stood for. Security guards patrolled the labs day and night. Visitors were banned without clearance. Engineers had to burn all test notes at the end of each day. In April, a new idea changed everything: shockproof vacuum tubes. The solution came not from a scientist, but from a young Navy machinist named Charles "Chuck" McKinney. Watching another failed test, he realized the filaments were breaking not from impact, but from vibration. He suggested suspending the tubes on tiny steel springs and filling the chamber with silicone oil to cushion the movement. The scientists laughed. It sounded primitive. But when they tried it, the tubes survived. Within a month, the team had its first stable circuit. The prototype was crude, a hand-soldered device wrapped in tape, but when fired from a test barrel, it came out intact. They added the radio oscillator, the miniature antenna coil, and a self-destruct mechanism that would trigger if the shell missed its target. That last part was essential. The Navy refused to risk an intact fuse falling into enemy hands. By June 1943, the project moved to field testing. The first live-fire range was at Dahlgren, Virginia. The scientists stood alongside Navy officers, their faces sunburned and eyes squinting against the glare. A small drone plane buzzed overhead, pulled by a cable attached to another aircraft. The order was given. The gunner loaded a 5-inch shell marked VT-3. The blast shook the ground. The observers saw a flash mid-air, not random, not distant, a precise detonation within 50 feet of the target. The drone's wing folded, and it spiraled into the bay. The silence after was louder than the explosion. The test officer turned to Tuve and said quietly, "You've just changed the war." The Navy immediately classified the entire project at the highest level. Even within the military, few were told what had been accomplished. Officially, it was just another fuse improvement. Unofficially, it was the biggest leap in weaponry since the machine gun. Tuve's team didn't celebrate. They knew success in a lab was meaningless unless it could be mass-produced. That was the next battle: industrialization. Each proximity fuse required components so small that existing factories couldn't build them. The vacuum tubes were a particular nightmare. Each one had to be hand-assembled under a microscope, with filaments thinner than a hair. The government turned to civilian manufacturers, RCA, General Electric, Westinghouse, and demanded production at a scale they'd never attempted. Thousands of women were recruited to solder the delicate circuits. They worked in shifts around the clock, their fingers blackened from flux and burns. One of them, a 20-year-old assembler named Grace Wheeler, remembered being told only that her work helps the Navy find things. She didn't know that each fuse she built would soon be sitting in a shell capable of defending entire fleets. To keep costs down, production was divided into stages across the country. The batteries came from Ohio, the vacuum tubes from New Jersey, and the final assembly from a converted piano factory in Connecticut. Every box was marked VT, shipped under armed guard, and tracked like gold. The process demanded perfection. A single loose wire could kill a fuse before it ever fired. Quality control inspectors were ruthless. If one unit failed a test, the entire batch was scrapped. Out of every 1,000 fuses, maybe 600 passed. That was enough. By autumn, shipments began arriving at naval depots, marked only with serial numbers. The sailors unloading them didn't know what made them special. They just saw ordinary shells, same weight, same paint, same steel casing. The first combat use was planned for December 1943 in the South Pacific. The Navy chose the USS Helena's sister ship, the USS Cleveland, to test the new rounds in real battle conditions. The officers received sealed envelopes labeled Top Secret, VT Authorization. Inside were simple instructions: fire as usual, observe the result, report immediately. On December 25th, Japanese bombers approached the fleet near Bougainville, the sky filled with the familiar thunder of anti-aircraft guns. The first wave of shells detonated as expected, random bursts in the clouds. Then the gunners loaded the VT rounds. What happened next was something no one had ever seen. The bursts began to cluster around the planes, not above, not below, but directly in their paths. The Japanese formation broke apart almost instantly. 3 planes went down in the first minute. The rest scattered in panic. The Navy's after-action report was clinical but stunned. Effectiveness exceeds all previous data. Estimated increase in hit probability, 400%. In practical terms, the fuse had turned anti-aircraft guns from noise into precision weapons. For the first time, a shell didn't need to hit an airplane. It only had to pass near it. Within weeks, production orders tripled. The government built entire new plants to meet demand. Engineers refined the design again and again until the unit cost dropped below $10. By mid-1944, American factories were producing 40,000 proximity fuses a day. The weapon secrecy remained absolute. Crews were ordered never to recover unexploded shells, and any proximity fuse that failed to detonate was destroyed on site. Sailors were forbidden from discussing the new rounds even among themselves. Commanders referred to them simply as specials. One officer joked, "If one of these lands on a Japanese beach, we'll all end up in Leavenworth." But the results spoke for themselves. Over the following months, the proximity fuse transformed naval warfare. Japanese pilots who had once mocked American flak now found the sky itself turning deadly. Kamikaze attacks that once guaranteed impact now ended in fireballs hundreds of yards away. What began as a desperate experiment in a Maryland lab had become the single most effective defensive weapon of the Pacific War. And yet, inside the applied physics laboratory, the scientists barely slowed down. They were already working on the next phase, adapting the fuse for field artillery, rockets, and anti-submarine warfare. Tuve himself rarely left his desk. When asked years later what he remembered most, he didn't mention the success, or the secrecy, or the medals. He said only, "We had a deadline, and it was measured in lives." Behind the calm tone was the truth no one said aloud. The proximity fuse wasn't a scientific triumph. It was an act of controlled desperation, a collision of physics, fear, and necessity that turned metal and math into something terrifyingly efficient. For the men at sea, it meant survival. For the engineers in Maryland, it meant responsibility. Because once you build a weapon that can think for itself, there's no going back. The fuse had started as a handful of glass and wire. By the end of 1943, it was rewriting the rules of modern war, and the people who built it were only beginning to understand what they'd unleashed. Winter, 1944. The war had entered its most brutal phase. On 2 sides of the planet, the proximity fuse was about to prove what it could really do. What began as an engineering experiment in a Maryland laboratory was now quietly packed into crates and shipped under guard across oceans. It bore no heroic name, no special markings, and no mention in the newspapers. Yet in the next 12 months, it would change the physics of the battlefield, from the forests of Europe to the islands of the Pacific. And in doing so, it would save more lives than any other single piece of technology in the war. The first to see its true power weren't sailors, but soldiers. In December 1944, the German Army launched its final offensive in the West. It was called the Ardennes Counteroffensive, later known simply as the Battle of the Bulge. Over 200,000 German troops surged through the snow-covered forests of Belgium and Luxembourg, crashing into thin American lines. Fog and sleet grounded Allied aircraft, giving the Germans the cover they needed. American units cut off from air support fell back under relentless pressure. On the ground, General Omar Bradley's artillery commanders faced a nightmare. conventional airburst shells were almost useless. The overcast skies made ranging impossible, and the snow buried shell craters before anyone could adjust fire. At Bastogne, surrounded American units were running out of everything: ammunition, food, hope. It was here that the proximity fuse arrived. The first batch of VT shells was delivered in unmarked trucks. The crates were labeled only with the words, "Special Fuse, handle with care." Few of the artillerymen knew what made them special. They looked like ordinary 105mm and 155mm rounds, same shape, same weight. The only difference lay hidden in the nose, a small radar brain waiting to sense metal, movement, or the faint echo of its own signal bouncing off snow, armor, or flesh. Colonel George Axelson, commanding the 406th Field Artillery Group, received the new ammunition with a warning from headquarters. Use only in dire emergency. Do not allow recovery of unexploded shells. Axelson, a practical man who had watched too many attacks slip through his defenses, didn't need convincing. By mid-December, his units were firing the first proximity-fused rounds in Europe. The results were instantaneous. Traditional shells buried themselves in the snow before detonating, their fragments swallowed by drifts. The VT shells exploded in mid-air, scattering shrapnel across open ground. German infantry, who had counted on snow cover for protection, were suddenly cut down by invisible bursts. Survivors described the new bombardment as ghost fire, explosions with no pattern, no warning, no sense of direction. The shells didn't have to hit anything. They only had to pass near. Within 48 hours, entire German regiments were broken. Prisoners later told interrogators that they thought the Americans had developed some kind of remote-controlled weapon. One officer reportedly asked his captors, "Where are your spotters hiding? The shells follow us even when we move." For once, the math was on the Allied side. Analysis later showed that proximity fuses increased artillery lethality by nearly 500% against exposed troops. That meant a battery that once needed 1,000 shells to neutralize an enemy formation could now do it with 200. The effect wasn't psychological. It was arithmetic. As the German advance stalled, commanders across the front demanded more VT ammunition. Eisenhower authorized its general use on Christmas Eve, calling it the most important development in the war against Germany. The timing couldn't have been more ironic. In Berlin, Hitler's staff still believed the Americans were short on supplies and reliant on obsolete technology. Within weeks, they learned that a single Allied artillery battalion equipped with proximity fuses could stop an entire division in its tracks. But the Ardennes was only half the story. Across the world, the Pacific War had entered its most desperate stage. Japan's Air Force, once dominant, was collapsing. The Imperial Command turned to a new weapon, pilots willing to die on impact. They called them Tokotai, the Special Attack Units. The Americans called them kamikazes. Each suicide plane carried a bomb or fuel tank and aimed to crash directly into ships. No flak gun, no fighter patrol, and no armor could stop a pilot determined to die. The psychological effect on sailors was devastating. They watched men steer planes through walls of fire, still holding course as wings burned and engines shredded. The odds of survival for ships hit by kamikazes were terrifyingly high for the attackers and devastating for the defenders. By late 1944, entire task forces were being crippled by single waves of suicide aircraft. Then the proximity fuse arrived. The U.S. Navy had already been using VT shells for almost a year in limited engagements, but Okinawa would be the first true test under full-scale attack. The island invasion began in April 1945, the largest amphibious assault of the Pacific War. Japan threw everything it had left into the defense, 1,800 kamikaze sorties in 1 month. The sky over the fleet became a living storm of engines and explosions. Aboard the destroyer USS Laffey, sailors loaded 5-inch shells marked VT. Each gun crew was trained to fire into the mass of incoming planes, not at specific targets. The proximity fuse would do the rest. The radar inside each shell measured the distance to the nearest metal object, wings, fuselage, propeller, and detonated at the precise instant when the fragments would cause maximum damage. In 30 minutes of battle, the Laffey fired over 300 VT rounds. Her gunners later described the scene as the sky tearing itself apart. Kamikazes that had once burst through conventional firewalls now exploded mid-dive, disintegrating before they could reach the ships. Out of 22 attackers that charged the destroyer, 11 were destroyed in the air, 5 splashed short of the hull, and 6 made impact, heavily damaged and off course. The Laffey survived, battered but afloat. Across the fleet, the statistics were staggering. In previous campaigns, it had taken nearly 2,000 shells to bring down a single attacking aircraft. With proximity fuses, the ratio dropped below 100 to 1. Over the course of Okinawa, American gunners destroyed more than 2,700 enemy aircraft, the highest kill rate of the entire war. Commanders estimated that without the VT fuse, at least half the invasion fleet would have been lost. The Japanese pilots never understood what had changed. Many believed the Americans had developed a new type of explosive gas or invisible barrier. Some assumed radar-equipped aircraft were directing invisible beams at them. They had no idea that the deadliest weapon in the Pacific fit in the palm of a hand. Inside the Navy's after-action reports, one sentence appeared over and over. The proximity fuse turned every ship into its own radar station. That wasn't an exaggeration. Each 5-inch gun, once blind and dependent on luck, now operated as a miniature detection system. Every time a shell left the barrel, it carried its own brain, a device capable of measuring distance faster than any human could think. By the summer of 1945, more than 22 million proximity fuses had been produced. Factories worked without pause, their assembly lines run mostly by women. The workers had no idea what their devices did. They were told only that the parts were electrical timers. In one factory, a supervisor gave a speech thanking his team for helping light the skies of freedom. Nobody realized how literal that phrase had become. The scale of production bordered on absurd. Each fuse contained 5 separate vacuum tubes, 3 resistors, 2 capacitors, and a miniature battery that activated upon firing. Every unit required more precision than a radio, yet they were built faster than any consumer device in history. The total cost per fuse fell to just over $9. At peak output, the U.S. was producing more fuses than the entire world had produced radios before 1939. The technology's impact spread beyond anti-aircraft defense. Field artillery commanders in Europe quickly realized that the same proximity mechanism could revolutionize ground warfare. Instead of burying shells in dirt or snow, they could detonate above the target, creating lethal airbursts that blanketed entire areas with shrapnel. In the Pacific, Marine Corps units used proximity-fused shells to clear ridgelines and cave networks. For the first time, artillery could reach enemies hidden behind cover. The effect on morale was dramatic. Soldiers who once feared enemy aircraft began to trust their own guns. Sailors who had braced for impact now fired with confidence. And commanders who had watched casualty reports rise month after month saw them finally fall. But not everyone felt triumph. Some of the scientists who built the fuse began to worry about what they had created. They had designed it to save ships, not to turn the sky itself into a weapon. In letters later declassified, Tuve and his colleagues expressed a mixture of pride and unease. One engineer wrote, "We gave them a brain for killing. I hope they never ask us to make it smarter." By the time the atomic bomb was tested in July 1945, the proximity fuse was already considered the second most important technological breakthrough of the war. Second, only because the world had never seen what came next. Yet in purely practical terms, it had done far more killing. Historians later estimated that proximity-fused ammunition accounted for over a third of all Japanese aircraft destroyed between 1944 and 1945. Even the scientists who worked on the Manhattan Project recognized its importance. When physicist James Conant briefed President Truman after the war, he stated flatly, "The proximity fuse, in terms of saved lives, may well have been the decisive factor in our victory." By the war's end, the fuse had found its way into every branch of the U.S. military. Naval guns, field artillery, anti-aircraft batteries, even rockets and depth charges. All were redesigned to use the same principle. The Army called it the VT miracle. The Navy called it our invisible ally. The Germans tried to capture one. They never succeeded. The Japanese never even learned how it worked. In all the chaos of the war, not a single unexploded fuse was recovered by the enemy. Every shell that missed had a built-in self-destruct. Every secret stayed buried. The proximity fuse had done what no general or strategy could. It changed the arithmetic of survival. The U.S. had turned timing, the smallest unit of war, into an advantage no one could match. When the guns finally fell silent in 1945, few of the men who fired those shells ever knew the names of the people who made them. They didn't know about Tuve's lab, or the solder burns on Grace Wheeler's hands, or the endless nights of failed tests in Maryland. They only knew that one day the sky that used to kill them had started killing back. In the official post-war assessments, the proximity fuse was credited with shortening the conflict by at least a year. That estimate was conservative. The numbers told their own story. American aircraft losses in naval combat dropped by 75% after its introduction. The effectiveness of anti-aircraft batteries increased sixfold. The cost per enemy aircraft destroyed fell from thousands of dollars to a few hundred. But beyond the statistics was something harder to measure. Belief. The sense that technology could shift fate, that human ingenuity could rewrite the odds. For sailors like Red Turner, who had once stared at empty skies and prayed, that belief was everything. In the months that followed, Turner's ship survived 3 major engagements without a single bomb strike. Each time he loaded shells stamped VT and watched the explosions form an invisible wall around the fleet. He never saw the radar pulses, never heard the circuits hum, but he could see the results. The falling planes, the burning wrecks, the saved lives. When the war ended, the Navy quietly declassified the existence of the fuse, but not its details. Newspapers mentioned it only in passing. There were no parades for the engineers, no medals for the women who built them. Tuve returned to academia. The factories closed or switched to consumer electronics. The world moved on to the next invention, the next conflict, the next secret. But in the silence that followed, something fundamental had changed. For the first time in human history, a weapon had used radar to decide when to kill. It didn't rely on aim or timing or even human judgment. It measured the world, made a calculation, and acted. It was still just a fuse, a circuit, a few tubes, a coil of copper wire. But it marked the beginning of a new kind of warfare, one where decisions could be made in microseconds, where machines would think faster than men, where technology would not just obey, but anticipate. The war had ended, but the future had already begun. And the tiny device that started it all was still sitting quietly at the heart of a shell, waiting to sense, to decide, and to detonate. August 1945. The war was finally ending, but inside the massive warehouses and factory floors that had powered it, the machines didn't know that yet. Conveyor belts still ran through the night. Women in grease-stained uniforms still hunched over magnifying lamps, soldering wires thinner than sewing thread. The proximity fuse, the little invention that had saved fleets and turned the tide of 2 oceans, was being made faster than ever. And even as Japan's surrender approached, the people who built it were only beginning to understand the scale of what they had done. The fuse had started as a lab experiment, a desperate attempt to hit what human eyes couldn't track. By 1945, it had become the foundation of an industrial empire. 35 separate factories across the United States produced parts for it, from Pennsylvania to California. At the center stood the VT Division, a secret program run jointly by the Navy Bureau of Ordnance and the Applied Physics Laboratory. Its headquarters looked ordinary, red brick buildings with blackout windows and no signs. Inside, 80,000 people worked under contracts so classified that even the plant managers didn't know the full purpose of their product. Every morning, thousands of women clocked in at 6 a.m. They wore cotton gloves, not to stay clean, but to protect the microscopic filaments inside the tubes from the oils on their skin. Each worker assembled one part, a resistor, a capacitor, a wire coil, over and over until muscle memory replaced thought. They didn't know that these were the same components that allowed a 5-inch shell to think, to sense, and to kill. Grace Wheeler, who had started in the assembly line 2 years earlier, was now a shift supervisor. She had built more than 10,000 units in her time. She knew how to spot a bad solder joint by smell alone. But she had never seen what her work actually did. The war was far away, and the secrecy was total. Her instructions were simple: build fast, build accurately, and ask no questions. In Maryland, Merle Tuve's team kept improving the design. Each new variant was smaller, tougher, and smarter. They reduced the number of parts from 130 to 80, redesigned the power source, and standardized the components so that any factory could build them without knowing what they were for. It was engineering stripped of ego, pure function, pure necessity. What made it work wasn't just the science, it was the system. The proximity fuse had forced the United States to invent a new kind of manufacturing, one that combined scientific research, industrial precision, and military secrecy into a single machine. No one person could see the full picture, but every cog in the process moved with the same urgency. It was, in every sense, an invisible machine, not just the fuse itself, but the nation that built it. By the time the war ended, over 22 million proximity fuses had been produced. They filled entire warehouses, stacked floor to ceiling in crates marked VT. Each crate contained the labor of dozens of hands, the ideas of hundreds of engineers, and the money of an entire country. The program had cost nearly $1 billion, more than the Manhattan Project, until late 1944. Yet, unlike the atomic bomb, the fuse left no crater, no signature, no moral debate. It simply worked, quietly and relentlessly, until there were no enemies left to target. When Japan surrendered on August 15th, factory whistles blew across the United States. Workers cheered, hugged, and threw their gloves in the air. For the first time in years, the production lines went still. But inside the APL, there was no celebration. The engineers stared at their benches covered in schematics and parts. They had been trained to solve problems under pressure, not to imagine what came next. For some, the relief quickly turned to discomfort. They began to realize what they had built, not just a weapon, but a principle, a device that didn't need to be aimed or timed, a mechanism that measured, calculated, and acted on its own. The proximity fuse was the first automated decision-maker in warfare. It made its own judgment call, when to explode, when to kill, without direct human control. That idea unsettled many of the scientists who had created it. Tuve himself, though proud of his team, often described the fuse as the beginning of a new kind of logic. When asked what he meant, he said, "It decides faster than we can. That's its strength and its danger." In the months after the war, the Navy declassified parts of the program to show the world how the Allies had won. Newspapers called it the miracle fuse. Journalists visited the remaining factories, interviewing the women who had built the components by hand. Photos showed smiling faces, but the captions told a different story. Phrases like secret work, never knew what they built, helped end the war. The truth was less glamorous. The proximity fuse had killed more enemy aircraft, soldiers, and sailors than any single weapon other than the atomic bomb. It had made the skies above Okinawa, the forests of the Ardennes, and the seas of the Pacific into invisible minefields. The enemy never saw it coming, and that was exactly the point. In 1946, when Congress held hearings on wartime technological achievements, the proximity fuse received little attention. The headlines belonged to the atomic scientists. Yet inside the Pentagon, senior officers privately called it the fuse that saved civilization. General George Patton had already said it during the war. The fuse is one of the three greatest inventions of this conflict, along with radar and the atomic bomb. He was right. The military immediately began adapting the concept for peacetime research and future conflicts. The same miniature radar circuits that detonated shells were soon guiding missiles and anti-aircraft rockets. The engineers at APL transitioned from building fuses to building control systems, sonar triggers, and even the first automatic flight stabilizers. The technology that had started as a desperate defensive tool became the blueprint for post-war automation. Tuve saw it clearly. In a 1946 memorandum, he wrote, "The proximity fuse has given us more than victory. It has given us the first practical demonstration that machines can make correct decisions in real time." That single sentence would shape the next 50 years of warfare. Meanwhile, the people who had worked on the production lines went back to ordinary life. Some found jobs in electronics, others in hospitals or offices. A few joined the post-war boom in consumer manufacturing. RCA, which had built thousands of proximity fuse tubes, retooled its factories to produce radios and televisions. The same workers who once built weapons now built entertainment systems. The irony wasn't lost on them. As one assembler later joked, "We went from killing noise to selling it." For the sailors who survived the war, the fuse became a quiet legend. Veterans told stories about how the new shells had saved their ships. They didn't know how the fuses worked, only that they did. One man described watching a Japanese bomber disintegrate mid-dive and said, "It was like the shell knew where he was going." Another said, "I didn't fire that one. It fired itself." Even decades later, those who had seen the proximity fuse in action spoke about it with a mixture of awe and disbelief. It wasn't just its effectiveness, it was the way it felt. For years, anti-aircraft gunners had fired blind, watching their shells vanish into empty sky. With the VT fuse, they could see the explosions follow the target. It gave them back a sense of control in a war that had taken nearly everything else. But the fuse had also changed something deeper, something invisible but permanent. It proved that war no longer depended on the reflexes of the human hand. The decisive moment could be delegated to a circuit. That logic, once unleashed, would never disappear. In the decades that followed, that same logic powered the Cold War. Guided missiles, radar homing torpedoes, automated intercept systems, all of them traced their lineage back to the fuse. Engineers didn't call it inspiration, they called it lineage. The same scientists who had worked under Tuve later helped develop the first surface-to-air missile systems. Others joined the RAND Corporation, where they designed early computer-based targeting models. Each innovation carried a piece of the same DNA: measure, calculate, decide. The proximity fuse had started as a defense against aircraft. By the 1950s, its descendants were making decisions about flight paths, detonations, and target tracking faster than any human ever could. The logic that once lived inside a 5-inch shell now lived inside intercontinental missiles. Tuve saw this with unease. In a speech at a post-war conference, he warned that the line between invention and automation will blur until the machine no longer waits for human confirmation. Few listened. The war had ended, the country was celebrating peace, and the world was racing toward the future. But inside military labs and think tanks, engineers were already designing systems that made the proximity fuse look primitive. In one sense, Tuve's invention had opened a door that could never be closed. Once you teach a weapon to think, it never stops learning. Back in Maryland, the original APL buildings still stood. The benches were cleared, the test guns removed, the blacked-out windows replaced with glass. The people who had once built the fuse now worked on weather radar, sonar mapping, and space research. Yet in the archives, the old blueprints remained, the circuit diagrams, the test logs, the sketches of shattered tubes. Visitors who looked at those papers decades later often struggled to understand how such a small device could alter the course of history. The drawings looked simple, lines, coils, a few notations. But each of those lines represented the first time humans had built something that reacted to the world faster than they could. The proximity fuse never had a famous photograph, never stood on a museum pedestal, and never carried the fear that followed the atomic bomb. But in its quiet way, it changed the balance of power forever. It was the moment when technology crossed the threshold from tool to participant. The Navy called it the invisible machine, not because it couldn't be seen, but because its influence reached far beyond the battlefield. It was invisible in the way it reshaped thought, how militaries, scientists, and eventually entire nations began to believe that machines could make perfect decisions. When the Cold War turned the world into a standoff of missiles and radar screens, the logic of the proximity fuse guided it all. The fuse had measured distance and detonated at the precise instant for maximum effect. The same principle now guided early warning systems, nuclear triggers, and defensive interceptors. Decades after the war, when automation became common in civilian life, traffic sensors, autopilots, even household electronics, they too carried echoes of the same principle. Measure, react, act faster than a person can. And yet, few remembered where that idea began. For Tuve, the fuse was never about victory. It was about solving an unsolvable problem, how to fight an enemy you couldn't see. He had once told a reporter, "We didn't build it to kill better. We built it so that human effort wouldn't be wasted." But the result was the same, a weapon that multiplied human efficiency to deadly effect. By the time he died in 1982, most of the people who had worked with him were gone, and the world had moved on to computers and satellites. But in every guided weapon, in every radar sensor, in every automated defense system, a piece of his original problem still lived: how to measure distance, how to know when the target is close enough, and how to act without hesitation. The proximity fuse had answered those questions perfectly. Too perfectly. That is why historians later called it the Quiet Revolution. It didn't end with an explosion. It ended with a calculation, one so accurate that the world never went back to guessing again. For the sailors who fired it, it was salvation. For the engineers who built it, it was a triumph. For the future, it was a warning. The fuse had started as a way to hit what men couldn't see. It ended as the foundation for every weapon that would ever see without them.